Hello everyone, Deep Learning with Python, chapter 9, and this time we will see some advanced deep learning for computer vision. So last time we saw the intro, and now we will see a bit more advanced techniques. The chapter contents, first of all, we will see different branches of computer vision. So image classification, what we saw before, image segmentation, object detection, and some secondary ones. We will also see some modern architecture, ConvNet architecture patterns. We used something very simple last time, like a stack of convolution layers. Now we will see what residual connections are, why they are helpful, what is batch normalization, what is depthwise separable convolution layer. And then we will use these in order to run some examples. And finally, we will see some techniques in order to visualize and interpret what the ConvNets actually learn. So let's get started. So the first part, the three essential computer vision tasks. So here are the main tasks. First of all, we have image classification. Again, what we saw before. It's when you assign one or more than one labels to an image. To understand what more than one could mean, here is an example. This is an example of single label multi-class classification. So what is label, what is class, what is symbol, what is multi? First of all, class refers to how many classes, how many categories we have here. So we see that we have, for example, 3 categories. Single label means that only one of these will label the specific instance, the specific image, for example. So here, only 1 out of 3 can be correct, and this is, in this case, biking. When we have multi-label classification, then we have multiple labels that we can use to tag the image. I think there is a microphone on. So in this example, we have, for example, both bike, person, and tree to be tagged as label in this classification problem. So this is the single label and multi-label classification. Then we have image segmentation. So image segmentation is, for example, when we try to segment an image into different areas. So we take the pixels of the image and we classify each pixel to a specific category. And then we have other things like object detection. So in object detection, what we do is that we draw some rectangles, a bounding box, around an object of interest in the image. For example, it could be around a person or around a bicycle. And of course, we have the tag, the class, the associated class with this rectangle. Some examples of all this, for example, for image classification, when you search something on Google Photos, then what is going on behind the scenes is that you're actually querying a very large multi-level classification model and one with more than 20,000 different classes, and then it returns the results on this. So this is a real life example of image classification. Image segmentation would be something like when you have this kind of color, like what I do right now, you see that my background is blurred. So what is actually going on is that my body is segmented and the background is segmented as another category, and that's why it can change the background or blur the background. And object detection, an example could be in self-driving, when you have, for example, the car, to use object detection in order to detect monitor the cars, the pedestrians, or the signs in order to make use of them for further processing. So these are some simple real-life examples of all these categories. And then there are other tasks, like, for example, image similarity scoring, where we have, for example, my face, and they want to make a face identification to see if my face is the same as one from a list of faces. In the database, key point detection, again, you want to detect specific key points, on the image, very useful, for example, when we try to identify a person. Usually we have some key points like the nose, the ears, the eyes, or the lips, or for pose estimation. Pose estimation is a specific categories. So we try to estimate what is the pose in 2D or 3D of a person, and 3D estimation. So there are many subcategories, but the three main categories for computer vision would be classification, segmentation, and detection. And here you can see some examples of segmentation. Again, each pixel of the image, and here examples of object detection. So you see bounding boxes around the objects. So let's continue. Let's see an image classification and an image segmentation example. There are actually two flavors for this. One is to segment the semantic segmentation, where each pixel is independently classified into a category, for example, cat and background, which means that all the cats will be labeled as cat. But there is also the instance segmentation, where we want to distinguish between individual objects, like, for example, cat1, cat2, cat3, etc. So this is more advanced. We will actually see an example of a simple, the usual vanilla semantic segmentation today. So let's see the example. Actually, right now, we will use this dataset, Oxford, for the pets dataset, which includes some 7,390 pictures of cats and dogs with segmentation masks. So you will see what the masks are like. We have three categories. We have the background, it's 0. The foreground, which is the actual objects, in this case the pet, for example the cat or the dog, and we have also the contour, so the line around the closed curve around the object. So first of all, we are supposed to download the data. I have already downloaded the data in order to save some time. I host them here, and this is in order to load the data. So let's start by running the code. What we have here is just the paths of the images and the targets. So nothing strange here. And this is how we will load an image and this specific image, for example, and we will plot it. So let's see what an image will actually look like. And this is one of the example images with a cat in the center. So, okay, I cannot scroll. Give me a second. So I can scroll. And this will be just a helper function in order to display the target. So the target, namely the mask, the segmentation mask. And here you can see what it looks like. Again, we have the object in one color, the contour around the object, second color, and of course the background. So now that we can see what it looks like, let's build a model to see what we can do. So let's see the code. First of all, we have to define some specifics like the image size. In this case, we will just load 200 by 200. We will shuffle them because we don't want only cats and only dogs again. So we have to shuffle with the same seed here, both the images and the masks. And then we will write this helper function. So path to input image, we just use the image to array that we defined before, and path to target, we just use the same function. And I mean, pretty simple. We just use grayscale here. What else we have? And then we just load all the input images and the targets. It's not that many, so we can load them in memory actually, and we break them to train and validation, as you can see here. So let's run the code. It will take some time. Actually, we can continue and it will load. So what I have done here is that I have, because this code takes time to read each image, I have saved the NumPy arrays and load the NumPy arrays. And here is the interesting stuff. So here we will define a model that will actually do the segmentation. So this is our first example of image segmentation using what we have learned and a new thing here. This is a function that gets a model where we pass the image size and the number of classes. Of course, we will use the functional API. So in the end, we have the model to be keras.model inputs and outputs, the tensors. We start with an input layer, so image shape plus 3. And then we have, first of all, the pre-processing. So we will take the 255, 0 to 255 unsigned integers. We divide by this number in order to have some from 0 to 1. And then we have a stack of convolution layers. So let's see what we have here. We have, for example, the first one. First of all, we start with 64 with a specific number, and then every a batch of 2 layers we double. So 128 and 256. All of them have a 3x3 kernel, so the size is fixed. And we use strides 2 at the first one of each block. So for this block, the first one is strides 2, which means that we will have half the size. And then next one keeps the same. Again, strides 2, the same, etc. Activation is always relu, and padding is same so that we don't change, we don't want to change. So this is the first part. We will see why we split in 2 parts. So the idea is that this part will encode the images. So the output of the last convolution layer will be an encoding of what this image is about. So all the necessary information for the segmentation. And then we have this thing, which is a stack of convolution D2D transpose. We will see in more detail what is this later on. The main idea for this is that you deconvolve, so you upsample this, whatever is the input. So for example, when you have something that is of specific size and you use this layer, this will upsample it when you use strides 2. And the idea is that we have again blocks of 2 of them. So 2 with 256, the next 2 128. So we follow the reverse order, and then 64 in the end. And again, 3x3, all of them, activation or relu for all of them, padding same, and every second of them we have strides 2. So it's more or less the reverse of what is the first part. And this is quite common. So you will see in segmentation, we have something that encodes and then something that decodes. In the end, we will use a simple conv2d with how many classes we have, softmax for the activation, and of course padding same. We build the model. So let's see what it looks like. And this is what the model looks like. We start with 200 by 200 by 3, and then we halve the size with 64, halve the size 128, again 256, until we reach a point where we start going, wait a minute. So yeah, so until, we drop this until we start going back to 50, 100, 200 in the end, and in the end we have the 200 by 200 by 3, which is the mask that we want to output. So that was for this. Now the idea for this is that it's the purpose of this encoding, as I mentioned before, that each spatial location or each pixel of this intermediate feature masks contains the information about a larger spatial chunk of the original image. And this is some kind of compression that afterwards we use this block to decompress it. Decompress it in a way that will be useful for the masks. So let's see one specific example of how this conv2d transpose works. So the idea is that, let's say we have an input from an intermediate convolution layer that is 100 by 100 by 64. And then we pass it through another convolution layer with 128 kernels, filters with stride 2, which means that we have this 100 to change to 50, and this 100 to 50, and for the number of channels of feature maps, we have whatever is here. Now, this will be the input shape to a convolution transpose. And what we can see here, for example, with 64 3x3 strides 2 padding shape. And what this does is that the output will be doubled. When we use stride 2, it will be multiplied by 2. So the 50 will become 8 and 100. And of course, the number of filters, the number of channels will be equal to the number of filters. So this is the main idea of convolution transpose, is to upsample in the same way that convolution with strides to downsamples. So let's continue to actually compile and train. Of course, I will not train here because, again, it takes lots of time. So the most complicated we get, the more time it will take. And here I just save the history and we will plot it. So the idea is that we have these kind of results, which are quite good. And here you can see that we start some kind of overfitting at this point, but up to this point, we are pretty good. And let's see what is the, what are the results, what they look like. For example, okay, I cannot scroll. So for this image, what we learned using this quite simple convolution, which is not very deep. I mean, it had something like 6 or 8 layers to downsample and this much to upsample. And you can see that it started learning something. Of course, there are many artifacts like this one or this one, but it starts getting the main idea. It starts getting that this is the object, the cut. The contour is more or less up to some point okay, and the background mostly is clear. So apart from these artifacts, we can see that it doesn't recognize something here. So for a simplistic model like the one that we saw before, it's not very bad. Of course, it can get way better. Now, what we saw before is, as I mentioned, quite simple, and there are actually some modern architectures that will save some problems, some issues that this kind of simple architecture have. So let's move on and see what this would be. So the main idea of the model architectures of the content, in this case the continent, is that what we try to do is make the problem simpler for gradient descent to solve. So the same way as we used different techniques to curate the datasets, if you remember, with specific kind of transformations that we applied at the pre-processing. And we apply these transformations because we have some prior knowledge regarding the data, the nature of the data and the nature of the information from the data that needs to be distilled. The same way the architecture, we try to make it simple using some prior knowledge on this. So what is the architecture? The architecture is actually the choices we make. For example, what kind of layers we use. For this category of computer vision, as I mentioned before, convolution layers are more or less the way to go. For other tasks, we will see it's some recurrent layers, for example. How we configure them, we will see some different architectures than just stacking them, for example. Or what arrangement we have in order to connect them. So all these choices is the architecture. And these choices define the hypothesis space that the model will try to search in order to have the final parameters. So for example, the convolution layers has the prior knowledge that the relevant patterns present in the input images are translation invariant, as we mentioned at the previous lecture. Now, regarding how we build them, how we build the models, it's this idea that it's actually not only for building neural network models, not only for building any software, but for building almost anything that has some complexity. And the main idea for this, the general idea is modularity, hierarchy, and reuse, which you can use from architecture to drawing to whatever. Here, how we use this is that the main idea is to structure the model in blocks or modules what we saw before was blocks of 2 layers, for example, that were repeating. And then we repeat them with a specific variation. For example, for VGT that we saw before, and is actually this one here, the main block is convolution, convolution, max pooling. And we take this and we just repeat it sometimes with different parameters. And the other idea is the feature hierarchy. So we want to go from simple features in computer vision to more complicated and distill the information. And this is why we have these pyramid-like structures. We have, for example, deep ones, and we get smaller in spatial dimensions. One thing regarding this is that, generally speaking, deep stacks of narrow layers performs better than shallow stack of larger layers. So this is one thing that we keep in mind, and we see this all the time. We have many, many layers. There is a limit, of course, on how deep you can stack your layers. You cannot, after you start stacking more and more layers, you will see that you have some issues. We start with, for example, with 32, then 64, then 128, the number of kernels, and we add layers, but how many layers we can add? So this is a question that when we saw this technique works, we wanted to answer. And we saw that you cannot just keep stacking layers. It doesn't work like this. So how we solve it and why this is an issue. So the idea is that when you keep stacking layers, you will have some problems with backpropagation. And here's the first concept that we will see for a bit more complicated architectures, the residual connections. So let's talk about the residual connection with an example. Maybe you're familiar with the game, the simple game, the telephone, where you have the initial message is whispered to the ear of the first player, of the second player, I guess the index, 0 index. And then you have the second player to whisper it to the third player, and then the third player whisper the same message to the next and the next player, and so on. And the whole idea of the game is that after a point, the message is completely destroyed. You cannot understand what was the initial message. And mathematically, you can see it like this. So we have an original input, a message, and we pass it through some functions, the first function, the second, the third, the fourth, etc. And every time we pass the information through some transformations, the information is changing so much that you cannot reverse the original information. And in our case, the problem is that if it's too deep, then the noise starts to overwhelm for the gradient of information, which means that backpropagation, the way we saw before how it works, stops working. The chain rule doesn't work that good anymore, which means that the model will not train, and we have what is called the vanishing gradients problem. So one way to solve this is the residual connections. So this architecture that we will see now, it's quite simple. It was introduced back in 2015. And it's a whole family of models, the ResNet family of models, very popular. They changed the whole way of doing computer vision with deep learning back then. It was developed at Microsoft by et al. So let's see what I cannot see. Okay. So let's see what it actually looks like. So the idea is to force each function in the chain to be non-destructive. And in order to do this, we add a noiseless version, noiseless channel for the information to flow through this channel. So originally we have the input, we have a block of some layers, and then we have the output. And if we've stuck many of these layers on many of this block, as we said, we will have a problem. So what we do is that we have this residual connection. And this residual connection that is added in the original helps so the gradient can flow, the information for the backpropagation can flow easier and without this destruction problem, this vanishing problem. What this would look like in pseudocode would be that we have some input, whatever it is from the previous block, for example, and then we assign it to a tensor residual. We pass this input through the block as we would do before, but we don't return this x, we return this x plus the residual, as you can see here. So again, the implementation is very simple. We'll see some variants, what happens if the shape changes, but the idea is simple, yet it's very powerful because this allowed to go very, very, very deep and to have way better results than before. And actually now all the architectures use some variation of this residual, even now, I mean, 10 years, 5 years later, more. So what happens if the output shape is different than the input shape? In this case, we can use one-by-one convolution to the layer with no activation that will reshape this x, this residual, to what the final x will look like. Let's see what happens, for example, when the number of filters changes. So this is an example of, we have the inputs, and then we have a convolution layer with 32, so we start with 3, and then we have 32 output channels in this X, and then we want to pass this X through this layer. So imagine that this layer is the block that we had in the previous image. So within the block, we see that the output will now have 64 instead of 32, which means that we cannot add this residual to this output because this residual has 32, this output has 64, so we cannot just run this line. What we do is what I mentioned before. We pass the residual, as you can see here, through a convolution that is one by one, so this number, and for the number of filters, we use the number of filters of the previous, of the input tensor, of this tensor. So after we take this new residual, we can apply the addition, otherwise we couldn't. So this is the simple thing that we add if we have different number of filters. Now let's see what happens if we have max pooling, so if we change the spatial dimensions. So in this case, again, very simple. We have the input, we have whatever is the previous layer, and this is our block. And what our block is what we had before, plus max pooling with window 2. What this makes is that whatever the input dimensions are, it shrinks to half height and width. So the only thing we have to change is that here we have to add these strides too, so that it will also, the residual will get halved. And then again, we can simply add them. So these are the three variations. Either we have the same one, so we just add it, or we have different number of channels, and different dimensions. So we add this one by one convolution and we solve it. Now let's continue and build an actual model using this technique. So the idea is that, again, we have the input layer, in this case 32 by 32, let's say, and we have this pre-processing layer, and this is the main block. So the idea, again, we will explain this, but the main idea is that we have some blocks, whatever they are. This is the main body of the model. You will see it very often. We define whatever the block with whatever parameters, and then we just make a chain of these kinds of blocks. And in the end, this is the output of the model. We always have a global average pooling for classification, and we have the dense layer, for example, in this case, and we build a model. So let's see this block. This block takes some input tensor, the number of filters, and if we apply pooling or not. So the idea is that we keep whatever is the input, and we pass this input tensor through two convolution layers. Again, the number of filters like this one, 3 by 3, activation or a loop, adding same. So pretty straightforward. Then if we want pooling, we apply pooling to this tensor, and we also apply a convolution one by one with strides to the residual. Otherwise, if we have changed the shape of the, the number of channels, the number of color channels actually, of the X, we have to change also for the residual, so we use that many filters one by one. And of course, in the end, we add the two tensors in order to return it. So this is what this architecture would look like. Again, we start with something like 32 by 32 in this case. We halve it, 8, and every time we increase the number of channels, the number of filters. And in the end, we have the global average pooling and the output. And this is what it would look like as a graph. So I hope this is okay. So this is more or less what the residual connection looks like in this specific model. We have whatever input, rescaling, the first convolution, and then we take, so here is the first block. This block of convolution max pooling, and here is the residual. We see here that we have 32 outputs, so this has also to have 32, as you can see here. And here we halve it, so we use a max pooling, which means here we halve it with strides to 2. And then we just add these two, and the addition doesn't change the shape, of course. And we have another one, here is the block, here's the residual, we have 64, we have half of it, and then we add. And here in the last one, we don't want to halve the size, we just have to double the filters. We add them, global average pooling, and the dense. So pretty straightforward, yet very powerful, this simple thing. Now, this would be one of the ways that we use in order to go deeper, to have deeper networks with more layers. Another way to solve the problem of getting deeper is the batch normalization. So let's see what batch normalization is. The idea is that, for example, when we start when we have the original input to the model, you saw that we make the magnitude of the values of the pixel intensity, for example, smaller. We start from 0 to 255, but we pre-process to 0 to 1 or 0 to something like -1 to 1, for example. So the idea behind this is that we want small values with small magnitude as input because it behaves better, the convolution layers behave better. So we follow the same idea, but now with the activations of the layers. So instead of because having small values as input doesn't mean that in the intermediate layers, the values will remain small. It can start exploding very big values, negative or positive or whatever, or very, very small and diminish. So the idea is that why not do the same as the normalization within the model, so in the intermediate layers. And one thing we can do is the very simple normalization with mean 0 and standard deviation 1, which will be something like this. So whatever data we have, we subtract the mean for specific axis, and we divide by the standard deviation. So this is exactly what this batch normalization layer does, and it does it for the whole batch. So if we have a batch of 32 images, let's say in this case, then when we apply this, it will take all these 32 images, the activations for these 32 input images of a convolution layer, for example, and it will apply this transformation to the activations of the previous layer. So this way, the values will be centered to 0 and will be more or less from -1 to 1 standard deviation, so not very, very big, maybe 2 or -2 or something like this, but it will be regularized. And this will help the gradient propagation flow better, the same way as the residual connections help in this. And again, this technique, we see that it allows for deeper networks, and it's actually something that is implemented also in modern architectures. Two things. One thing is that we don't need to use bias. So this is an example of how we call the layer, by the way. We have whatever X, we pass it through a convolution, and then we apply batch normalization. First of all, you see here, use bias parameter to be false, because either way, the output of the batch normalization will be centered to 0. So it doesn't matter if we add something, we just save one parameter. The second thing is the activation. So there are different approaches here. You can either have the activation here before the patch normalization, or you can have it after. The author of the book proposes to have it after, but it's not that it will change the result significantly. So it's not very clear if it's better to have it before or after. There is some explanation why after would be better, but again, you can do whatever you want actually here. So these are two methods to go deeper, again, residual and the patch normalization. And there is a third thing that we can use, and we will see now, is the depthwise separable convolutions. So the idea behind this is that we can actually replace the COM2D layers with another layer that will be lighter, which means that we will have fewer trainable parameters and fewer floating point operations. And the result might actually be quite better, the performance. So how can we do this? I mean, it sounds pretty cool, right? The idea is that we perform a spatial convolution on each channel of the input tensor independently. So instead of having all the layers of the tensor, of the channels of the tensor to be processed through the convolution layer, we break it to channel by channel, as we can see here. So we have the input, whatever input tensor is, and then we split the channels. So let's say we have 64 channels, okay, feature maps. Then instead of treating all of it as one thing and make many computations, we break it to 64 of them, and then we apply a point-wise convolution. It could be, for example, 1 by 1 convolution, or here it could be 3 by 3. And then we take all of them, the 3.3, we concatenate them, and then we apply this point-wise convolution, which will be 1 by 1, to have the number of output channels that we want. So what is the assumption behind this architecture? The assumption is, for example, that the spatial locations in the intermediate activations, be careful here because we don't use this as the first input with the 3 channels, because the 3 channels are very tightly connected to each other. Information in one channel is heavily related to the R channel with the G channel with the B channel, okay? But afterwards, each filter learns its own thing, its own feature, which means that the first filter of a convolution doesn't have to do anything necessarily with the fifth filter. It might learn complete different patterns. And this is the idea that these intermediate activations are highly correlated spatially, but not channel-wise. So channel-wise, they are highly independent. Again, this is the idea. We split the channels, we pass each channel separately, each feature map, we concatenate them, and then we apply point-wise 1 by 1. So let's see what we can do if we put all of them together to make a quite better model, which is something like the exception model. And the exception model is actually a model that was produced by the author of the book, François Chollet. So here is what we are going to do. First of all, the idea is to organize the model into repeated blocks, as we saw before. So we will have a specific thing that will be the main block, and then we will repeat, code this block again and again. Number of filters we increase as we go deeper, and the spatial feature maps decrease, so we have to downsample. Again, deep and narrow, better than broad and shallow. This is a mantra for this kind of networks. Residual connections, we will use them because they help, but normalization, we will use this. And we will actually replace convolution with separable convolution 2D, but you can have the same exactly with convolution, it doesn't change something. Now, so this is for the data. We will use the cats and dogs, the small one that we used actually last time. So I have already downloaded and split it. So here we just create the datasets. Again, 2,000 for training, 1,000 for validation, 2,000 for testing. This will be our data augmentation, so pretty straightforward. Random fleet, random rotation 10%, and random zoom 20%. Nothing new here, and here are some new things. So again, we will use the functional API. So in the end, we have the inputs and the outputs. We start with inputs 180 by 180. We pass this through the data augmentation layers, this small model, and then we will have the pre-processing, so rescaling, and we start with this convolution. So again, no separable convolution at the beginning because we have three tightly interconnected channels. We will use a big kernel size here. We want a bigger information of bigger patches, and we will not use bias to any of them because we will have the layer, the batch normalization layer afterwards. And here what we do is that we take this and we go through this block here this many times. So we start with this many layers, 64, 100, and we double each time. So first of all, we assign this to residual in order to add it in the end. And we have these blocks. So two blocks of batch normalization, activation, and convolution, separable convolution. Always loop activation, adding same 3 by 3 and whatever size we have. We start with 32, for example. And again, we don't use bias because we have another batch normalization. Again, activation, another separable. So in the end, we have a max pooling. And the max pooling is used to downsample, so strides 2, we halve the size. And the residual, we pass it through one by one with the same number of filters as the last one. And strides 2, again, because we use this max pooling. Padding is always the same. And we don't use bias because we will use batch normalization afterwards. We apply this on residual and we add the X and the residual. We repeat it many times, and in the end we have, of course, global average pooling. We added dropout just for helping the training, and dense with one output, cat or dog, and we build a model. So if you get familiar with how this general idea of blocks works, this is pretty straightforward, actually, pretty simple. So let's see what this would look like if we would train it right now. And this is what this would look like. We go quite good, so we don't have that much problem with overfitting, as you can see here. We have some overfitting, but not like this. There are, of course, the spikes. This is something quite common in big networks. But the idea is that we have good performance. So the new model achieves a test accuracy of more than 90% when comparing to the previous one with just vanilla convolution layers and maybe dropout or something like this that we have had 83.5. So pretty impressive. I mean, again, these numbers, this difference in numbers is pretty big, even if it doesn't seem so. So following these architecture best practices, it does have, as you can see here, some sizable impact to the model performance. Again, what we did is that we added these two, let's go back. We added using the batch normalization, and we used this residual, so these two big things, and we replaced convolution with separable convolution. So these small things had big impact. Now, so this was the part, the first part, big part on how we can implement something for segmentation, how we can implement something that can go deeper, again, using these two actual things. And if we want the third one, the separable convolutions. And we can apply the same pattern, build big models also for segmentation as the same thing we did before, we can do it with these techniques. Now, the second part that we have some 10-15 minutes, so it will be mostly for how we can interpret what the model learns. And interpretability is actually quite important for computer vision applications for various reasons. For example, let's say that we have a model, a classifier, and classifies the image of a truck as a fruit. So we want to know why, what happened, what did the model see in this, what kind of patterns in order to output this thing. Or for this is actually quite important when you have a model to complement human expertise. And a very specific example is whenever we use deep learning for medical imaging. And why this is a problem? This is a problem because the doctor cannot just get a model that says, okay, this is, for example, tuberculosis. They need to know why it is. They need to know what the model found in this. And also the developer needs to know if the model actually finds something or it finds nothing related to what it's looking for and just outputs the correct thing. And there are different approaches, different techniques in order to do this. Due to time limitation, we will only see the last one. And actually the last one is the one that is mostly used. Well, this could be helpful for some people, but personally, I don't find them that helpful. One is visualizing the intermediate ConvNet outputs to see what are the intermediate outputs, visualizing the ConvNet filters. So this is more or less to see what are the patterns that activate these specific filters. For example, it's activated mostly by lines like this or by this kind of, or more complicated things like faces of dogs. For me, the most useful is the last one, visualizing the heat maps of class activation in an image. So let's see how this works. So the idea is called the class activation map visualization, and the idea is to produce the heat maps of the class of activation over the input images. So let's say we have an image, and what we want is to take the activations of the last layer, for example, the last convolution layer, and make a 2D grid of the scores that are associated to the specific class that we are looking for. For example, if we have a dog versus cat, we can generate the images of what is more cat-like parts of the image or more dog-like parts of the image. And this allows us to debug the decision process and to locate specific objects in an image. Actually, this last one is useful because you can technically have a segmentation model, more or less, when you just have a classification annotation. And it's actually used also in the industry. So if you don't have segmentation annotation, you can build a classifier and you can use this in order to see, okay, where is it more or less the object we are looking for. And this is how it works. The idea is that we take the output feature map of a convolution layer, usually the last one, for a specific input image. And we take this output feature map and we weight every channel based on the gradients for the specific class. Let's see in code how this works to understand a bit better, because it's not very clear, I guess, right now. We will use exception in order to do this, and we will process a specific image. So here is just a helper function to load the image, nothing special. Again, so let's see it because it's not very difficult. So we load the image to array. This thing is to expand the dimensions because we want a batch, again, not a simple image, a single image. And this is the pre-process that has to be done for the specific model. Again, we don't have to know, we just apply this. We take the image array with target size 299 by 299. And because this is from -1 to 1, if we want to plot it, we have to apply this transformation here. So this is just an image of 2 elephants. Now let's see how we can see what the model, where it focuses in order to identify that these are elephants. First of all, the predictions of the model. We have the top 3 results. We have most likely to be an African elephant. And the actual class of this African elephant is the class 300 with index 386. So now let's see how the model finds that is this specific class. First of all, we take the last convolution layer. The name of the layer, the last convolution, is this one. So we just get the layer and we assign it here. And then we build a model with whatever the model inputs are, and as output, the output tensor of this layer. So this model is from the beginning until the last layer of the model. And then we want the second part, which is the classifier. So the classifier, first of all, the input would be what is the output of this, more or less. And then we want also these 2 layers, that is the average pool and the predictions. So we take this classifier input and we pass it through these 2 layers. So we pass through the model.get layer, this layer name, and we apply it on this tensor. So now this will be the final output classifier tensor. And we build a classifier model that takes whatever is this input, the output of this model, and the output of the classifier. So if there is an earthquake. So if we connect these 2, then we make the original model. Now, retrieving the gradients, and this is the important part, how we can retrieve the gradients on top of the predicted classes. We use the gradient tape, of course. So we take the output of the image array through this convolution layer model. This is the output. We have to watch it in order to retrieve the gradients, and then we pass this output through the classifier model. So this would be usually our predictions, the classes, the elephant, for example. But what we actually want is the gradients of this. So we get whatever is the correct, the most probable class. This is how we get the 386 in the previous case. And what we want is to have the all the predictions for the specific top pred index, so for the specific index. So we take this and we get the gradients of this with respect to the last convolution output, this one. So this is what we are going to use. Again, the output of the convolution, of the last convolution, we get the gradients with respect to the class, the most probable class. And let's see how we use these grads. So the idea for this is that we take these grads and we apply a reduced mean. So this is something like, I don't know, 8 by 8 by, okay, the first is but, so 1 by 8 by 8 by 2048. And by reducing mean, we have 1 number per channel. And these numbers, 1 number per channel, will be the weights. So we take these 2000 something numbers, and we also have the last convolution layer output dot numpy. We get the array 0 because we have buds, so we want the single image. And this is the output of the last convolution layer, which is again, it's 10 by 10 by 2048. And what we want to do is to take all of them and to weight them based on these numbers. So for each feature map, we take the feature map and we multiply it by the corresponding number, the corresponding weight. And then we take all of them and we just take the mean, the average. So here we have again 10 by 10 by 2048. We average them, so the output will be 10 by 10. And this 10 by 10 will be the weighted thing that we need, the weighted activations. And these weighted activations will be just a 10 by 10 grid of whatever we are looking for. It will look like this. So these are the activations of the last layer, the last convolution layer. And this is the information that the model actually uses in order to predict class 386. This is how we know where the model focuses. And this is just some boilerplate code in order to take this 10 by 10, enlarge it, put colors, and put it in the same image as the input image. And the final output will be something like this. So here we can see the original image with the areas that the model focuses mostly. And this technique is actually quite useful because we can debug a model with this. For example, it's been, especially in medical images, and that is my field. I mentioned it before, it's many times that the model focuses on whatever it can find to predict the correct class. So it can focus on a letter that there is at the top right or top left of the X-ray, for example. And if you have some strange results, you can use a technique like this to see, okay, the model focuses here, but the problem is in the lungs. So there's something wrong going on. So this is actually quite a useful method to debug the training process. In this specific example, it's interesting because we can see that the model focuses quite heavily also in the ears of the elephants, which might be because the model has to distinguish between, for example, African or Indian elephants. So it focuses at the correct parts. If it would focus, for example, here, we would know that it uses the environment of the elephants to understand what kind of elephant it is, but it doesn't in this case. So that would be more or less for this chapter, for this session. Let's summarize. First of all, we saw the essential computer vision tasks, three main categories: image classification, image segmentation, and object detection. Each one of them with specific users, as we saw in real life. We also saw some best practices that will help us go deeper. So residual connection for the flow of the gradient, batch normalization for keeping the values in whatever range we want, and depthwise separable convolutions that slightly improves the performance and has less memory and less floating points. It doesn't get faster though, and it has to do with the NVIDIA kernels. It's a different discussion. Representations that ConvNets learn are easy to inspect. We usually say that deep learning models are black boxes. They are not entirely black boxes. We can see there are techniques like the one that we described that shows you what's going on inside. And one of them was to generate the heat maps of the class activity. Again, very useful. That would be all for this presentation. Thank you very much.